In the previous lecture, we have studied about the classification of semiconductors on the basis of the nature of atoms. So, semiconductors are classified as elemental and compound semiconductors. In this lecture, we are going to study about another classification of semiconductors, that is intrinsic and extrinsic semiconductors. So, before we discuss about the classification, we should know what is meant by doping. So, doping means it is the process of adding impurities to a semiconductor. The process of adding impurities to a semiconductor is known as doping. So, a semiconductor can be in pure form or impure form. Impure form means doped semiconductors. If you add some impurities to a purest form semiconductor, then that semiconductor will become impure. That, or otherwise we can call it as doped semiconductors. So in this lecture we are studying about the classification on the basis of the impurities. So actually the semiconductors in pure form, so semiconductors in pure form are known as intrinsic semiconductors, and the semiconductors in impure form or doped form, that is doped semiconductors are known as extrinsic semiconductors. So these are the two classification of semiconductors, that is purest form semiconductors and the impure form or the doped form, that is known as extrinsic semiconductors. Actually we can classify the solids as insulators, semiconductors and conductors. We are dealing here only with semiconductors. So actually if we consider an insulator or semiconductor or conductor, there will be a conduction band and valence band. Actually that is the topmost band, that is known as the conduction band, and the bottom band, that is known as the valence band. Normally the valence band will be completely filled with electrons and the conduction band will be empty. And the difference between the conduction band energy and the valence band energy level is known as band gap or forbidden energy gap. So the difference between the conduction band energy and the valence band energy, that is known as an energy gap or the forbidden energy gap. So we should know the conduction band is normally empty and the valence band is completely filled with electrons. So normally this valence band is normally called completely filled valence band, and the conduction band is normally empty conduction band. So according to the energy gap, we can classify the solids as insulators, semiconductors and conductors. So if we look at the insulators, the energy gap is much greater than that of semiconductor. So a lot of energy is required to excite the electrons from valence band to conduction band. So if some electrons are available in the empty conduction band, then that material will conduct. Here the band gap is very high, so the electrons cannot excite to the conduction band. So the probability of finding electrons in conduction band is very less. So to overcome this high energy gap, a lot of energy should be applied. So such type of materials are known as insulators. But in semiconductors, normally the energy gap is less than 1 electron volt or approximately 1 electron volt. So here the electrons can excite to the conduction band. So if we apply some energy, then the electrons from the completely filled valence band can excite to the conduction band. So there will be some electrons in the conduction band and this will be in conducting mode. So semiconductors are partially conducting devices and their energy gap is very less. Example, silicon, germanium. So the band gap of silicon is 1.1 electron volt. So normally the energy gap is usually specified in energy gaps. Energy gap value is specified in electron volt. That is the unit of energy. And in conduction band, in conductors, normally the conduction band and valence band are overlapped. So there will be free electrons in the conduction band. So it will be always in conducting state. That is the difference between insulators, conductors and semiconductors. So this classification is based on the energy gap. So we should understand what is conduction band, valence band and energy gap. That is very important. So in this lecture we are dealing about the intrinsic and extrinsic semiconductors. So the semiconductors part is we dealing. So the semiconductors are classified as intrinsic and extrinsic, and the purest form semiconductors that is known as the intrinsic semiconductors. And if we dope the intrinsic semiconductor, so if we dope the intrinsic semiconductor, we will get the extrinsic semiconductor. Extrinsic. So intrinsic on doping, we will get the extrinsic semiconductors, and this extrinsic can again be classified as N-type and P-type semiconductors depending upon the doping or depending upon the impurities we are adding. We can classify the extrinsic semiconductors are N-type semiconductor and P-type semiconductor. So doping means it is a process of adding impurities. The process of adding impurities is known as doping. And now we go in detail about the intrinsic semiconductors and extrinsic semiconductors. So actually the intrinsic semiconductors are purest form semiconductors. Intrinsic semiconductors are purest form semiconductors. Purest form semiconductors. Pure semiconductors are known as intrinsic semiconductors. So pure means no impurities are added to this semiconductor. For example, a normal silicon crystal, a silicon semiconductor or a silicon crystal or a germanium crystal can be taken as the example for purest form semiconductors. So actually the silicon is extracted from silicon dioxide. So we are studying in VLSI the various steps for purification. So we are extracting the sand or silicon dioxide, and we are getting the purified silicon wafers. And this pure form semiconductors, this pure form silicon wafers are known as intrinsic semiconductors. Actually, this is the structure of a silicon crystal at T is equal to 0 Kelvin. So absolute 0 Kelvin temperature, the structure of a silicon crystal. So we know the valency of silicon. The silicon atomic number is 14, that is 284. The valency will be 4. So each silicon atom consists of 4 valence electrons. So 4 valence electrons. So for every silicon atoms there will be 4 valence electrons. Each silicon atom, outermost electron of each silicon atoms form covalent bond with the neighboring silicon atoms. Covalent bonding means sharing of electrons. So each silicon atoms forms covalent bond with the neighboring silicon atoms. So if we look at this pure silicon crystal, so crystal means a periodic arrangement of atoms. So the silicon atoms are arranged in a periodic manner, and each outermost silicon atoms are overlapped or it is shared with the neighboring silicon atoms. So if we look at the structure of silicon at T is equal to 0 Kelvin, we can see all the outermost electrons of each silicon atoms are shared, or it forms covalent bond with the neighboring silicon atoms. So there are no free electrons. There are no free electrons at T is equal to 0 Kelvin. So we will have a doubt that this is intrinsic semiconductor, and T is equal to 0 Kelvin. There are no free electrons. So how it will conduct? So we are saying that at T is equal to 0 Kelvin, this semiconductor will act as at T is equal to 0 Kelvin. At T is equal to 0 Kelvin, the intrinsic semiconductor will act as an insulator. That is an important point. At T is equal to 0 Kelvin, it will act as an insulator since there are no free electrons. Since there are no free electrons, it will act as an insulator. So the next figure, it is at T is equal to some other temperature or 50 Kelvin. So if we increase the temperature of the semiconductor, or if we start heating the semiconductor, we can see that the covalent bond will break. The covalent bond will break, and this electron will become free electron. So the different covalent bonds, that is the shared bonds, will break and the electrons will become free. So these are the free electrons. These are the free electrons after the temperature is increased. So this electron become free, and actually now a new concept will come, that is known as hole. That is, the vacancy is created when an electron becomes free, and this vacancy is known as hole. So if we look at this structure at T is equal to 50 Kelvin, we can see that an electron hole pair will be formed by breaking these bonds. So, and also the number of electron concentration will be same as the number of hole concentration. The value of electron concentration and hole concentration is very same, and that is, if there are 4 electrons, there will be 4 valency free electrons. There will be 4 holes. So the electron hole concentration will be same as hole concentration for an intrinsic semiconductor. So at any other temperature, at T not equal to 0 or T equal to 50 Kelvin, the electron concentration is equal to the hole concentration. For an intrinsic semiconductor, the electron concentration will be equal to hole concentration. The electron concentration is represented by N and the hole concentration is represented by P. So these are the two important points we should understand from intrinsic semiconductor. At T is equal to 0 Kelvin, it will act as an insulator. At T is equal to 50 Kelvin or 100 Kelvin, so or any other temperature, the electron concentration will be same as hole concentration, since the electron hole pairs created are in equal numbers. So the concentration of hole and electrons will be same. And the third figure shows the energy band diagram of intrinsic semiconductor, and this is at T is equal to 0 Kelvin, figure A, and figure B, T is equal to 50 Kelvin or any other temperature. So we know that at T is equal to 0 Kelvin, it will act as an insulator. So at T is equal to 0 Kelvin, the valence band will normally be filled with electrons and the conduction band is empty. The electrons from valence band cannot excite to the conduction band. So if you look at the structure, you can see there will not be any free electrons in the conduction band. So at T is equal to 0 Kelvin, and this will be an insulator. There are no free electrons in the conduction band. At T is equal to 0 Kelvin, this will act as an insulator. And at T is equal to 50 Kelvin, we can see the electrons are exciting the conduction band. So here we can see 3 electrons are exciting to the conduction band. So there will be 3 electrons in the conduction band, and similarly, normally the electron hole pair means there will be 3 holes in the valence band. The electron concentration in the conduction band will be same as the hole concentration in the valence band. This N value will be equal to P value. The electron concentration will be same as the hole concentration. The N value will be same as the P value at T is equal to 50 Kelvin or any other temperature. From the structure we can see the electron hole pairs are formed due to the breaking of covalent bonds. That is explained with the help of this band diagram. That is, the electrons are exciting from valence band to conduction band. The electrons are exciting from valence band to conduction band due to the energy, the external energy that is T is equal to 50 Kelvin that we applied. So the semiconductor is getting some energy, and the electrons are exciting from conduction band to valence band. So valence band to conduction band, and the electron hole pairs value will be same. Electron concentration will be same. So these are the energy band diagrams at two different temperatures. That is, T is equal to 0 Kelvin and T is equal to 50 Kelvin. So we can draw in general the energy band diagram of an intrinsic semiconductor as this is EC, and this is conduction band energy EC, and valence band energy EI. So this is EC, conduction band energy, and this is EV, the valence band energy, and the middle level is known as EI. EI is known as intrinsic level. So intrinsic level means it shows that the electron hole concentration will be same. So EI will always be in the middle of the band gap. So between EC and EV, in the middle, we can draw another energy level that is known as EI. EI is known as intrinsic energy level. So EI indicates the value of electron concentration and hole concentration will be same for an intrinsic semiconductor. So this is the energy band diagram we are using in the coming lectures. So this is the energy band diagram of intrinsic semiconductor. So EC, EI and EV. Also, so some equations are also coming in intrinsic semiconductor. That is, if a steady state carrier concentration is made, then there must be some recombination of electron hole pairs at the same rate at which they are generated. So some recombination will occur. Some recombination will also occur in the energy band diagram. That is, recombination means the electrons from conduction band will come and occupy the holes in the valence band. So recombination occurs when an electron in conduction band make a transition, and this recombination can be direct or indirect to the empty state. That is, empty state means the hole in the valence band. So we have to consider the recombination rate also. And if we consider the recombination rate and the generation rate means the electrons are exciting from the valence band to conduction band, and recombination means the electrons from conduction band come and occupy the holes in the valence band. So at equilibrium, we can say that the recombination rate Ri is same as the generation rate. So at equilibrium, the recombination rate will be equal to the generation rate. Also, these processes are temperature dependent. So at any temperature, the recombination rate Ri will be proportional to the product of electron and hole concentration product. That is, Ri is proportional to N0 into P0. N0 is the electron concentration, P0 is the hole concentration. That 0 indicates N0 and N0 indicates that 0 indicates equilibrium condition. So at equilibrium, at any temperature, the recombination rate is proportional to N0 P0 product. So, and this recombination rate can be replaced by a constant alpha R. So Ri is proportional to N0 P0, that is equal to alpha R into N0 P0, where alpha R is the constant of proportionality that depends upon the mechanism of recombination, direct or indirect, or we can say it is recombination rate, and Ri is equal to alpha R into N0 P0, and this is same as alpha R into Ni square. Ni means it is the it is the intrinsic carrier concentration. In the intrinsic semiconductor, for an intrinsic material we have studied, for an intrinsic material the electron concentration is same as hole concentration, that is equal to Ni. So for an intrinsic material we can say that the electron concentration is same as the hole concentration, that is commonly represented as Ni. So Ni is the intrinsic concentration. Ni is intrinsic concentration. All the values of N0, P0, Ni are represented in centimeter raised to minus 3. So the value of Ni, so the value of Ni for silicon, the value of Ni, we should study the value of Ni for silicon. The value is 1.5 into 10 raised to 10 silicon atoms per centimeter cube. So the value is 1.5 into 10 raised to 10 atoms per centimeter cube. So this is the value of Ni. Ni means the intrinsic carrier concentration, and this relation N0 P0 is equal to Ni square. We are deriving it in the next lectures. So this is the relation Ri is equal to alpha into Ni square, and also we studied that at equilibrium this recombination rate will be same as generation rate. So these are the relations or equations dealing with intrinsic semiconductor, that is at equilibrium the generation rate is always equal to recombination rate. That is, if you are maintaining a steady carrier concentration, we have to consider the recombination rate also. At any other temperature, the value of recombination rate will be proportional to the product of electron concentration and hole concentration, and it is replaced by that proportionality is replaced by a constant, that is alpha R, that depends upon the mechanism of recombination, and which is equal to alpha R into Ni square. Ri is equal to alpha R into Ni square, which is equal to Gi. Gi is the generation rate. So you have to study the value of Ni of silicon at equilibrium. At equilibrium the value will be 1.5 into 10 raised to 10. And next we are going to study about intrinsic semiconductor is over. So next we are going to study about the second classification, that is extrinsic semiconductor. Extrinsic semiconductor means doped semiconductors. So doped semiconductors are known as extrinsic semiconductors, and it can be classified as N-type and P-type. So it can be classified as N-type and P-type. N-type and P-type classifications are based on the doping impurities we are adding. So N-type and P-type classification. So N-type means if an intrinsic semiconductor is doped with pentavalent impurities, so we will get N-type semiconductor. So an intrinsic semiconductor is doped with pentavalent impurities, we will get N-type semiconductors. And similarly, an intrinsic semiconductor doped with trivalent impurity, we will get the P-type semiconductor. And the example for pentavalent impurities, we should study the example for pentavalent impurities and trivalent impurities. This is very important in doing the problems of the module 1. So pentavalent impurities, example phosphorus, arsenic, antimony, these are the main pentavalent impurities. And similarly for trivalent impurities, boron, aluminium and gallium, indium. So pentavalent impurities means valency will be 5 and trivalent impurities means valency will be 3. So on doping a semiconductor, a purest semiconductor or intrinsic semiconductor with pentavalent impurities, we will get an N-type semiconductor. And on doping An intrinsic semiconductor with the trivalent impurity, that is example boron, aluminum, gallium, we will get p-type semiconductor. Here we are discussing about n-type semiconductor, and this is the structure of an n-type semiconductor at T is equal to 0 Kelvin, similar to that we studied in the intrinsic type. So here the silicon atom, a silicon semiconductor, is doped with pentavalent impurity. Pentavalent impurity means phosphorus. Example, phosphorus. So a silicon semiconductor is doped with phosphorus impurity. Only one silicon atom, one phosphorus atom is added here. So into a silicon crystal we are adding phosphorus atoms. So actually the valency of phosphorus is 5. So the valency of silicon is 4. So each silicon atom will form covalent bond with the neighboring phosphorus atoms. So here all the 4 electrons of valence electrons of phosphorus is shared with the neighboring silicon atoms. But the 5th electron can't share with the neighboring silicon atoms, so it will act as a this will act as a free electron. So for an n-type semiconductor, if we increase the doping concentration using phosphorus, if we add so many phosphorus atoms, the number of free electrons will increase. So for an n-type semiconductor, the majority carriers will always be electrons. So this is showing in the first energy band diagram at T is equal to 0 Kelvin. T is equal to 0 Kelvin. We can see the valence band. This is the valence band and this is the conduction band. The valence band is filled with electrons and the conduction band is empty. And here one additional energy level is showing. This energy level indicates the impurity level, the amount of impurity concentration we added. So that is level is represented by ED, and this level is also known as donor level. So the impurity we added is known as donor impurity. Donor means an extra electron is generated. So donating state, that condition is known as donor. One electron is extra. So this indicates, ED indicates the donor level. And this indicates the amount of impurity. That is, here we are adding phosphorus. So the amount of phosphorus atoms added is represented by this impurity level. So here 4 phosphorus atoms are showing the free electrons. And one more thing, this n-type semiconductor, the impurity level ED or the donor level will be closer to the conduction band. Since free electrons are present in the impurity level, this energy level is closer to the conduction band. This is the case at T is equal to 0 Kelvin that we discussed in the structure. So if we increase the temperature from 0 Kelvin to 50 Kelvin, then in the structure we can see that this electron is free, so it will excite to the conduction band. And if we keep on increasing the temperature, then the covalent bond will break. This bond will break and a free electron will be generated here and a hole will be generated. So if we keep on increasing the temperature, more number of electrons will be generated and some holes will be created. So if we see the structure, we can see that there are 2 electrons and 1 hole. So if we increase the temperature, then more number of free electrons will be generated and some minority carrier hole will be generated. So this is showing in the next figure. That is, if we increase the temperature, from 0 Kelvin to 50 Kelvin, first these electrons, the electrons closer to the conduction band will excite to the conduction band. These electrons present in the ED level, energy level, will excite to the conduction band. If we keep on increasing the temperature, then more number of electrons will excite from valence band also. So the electron concentration in the n-type will be very high, and we can see some holes will be created in the valence band due to the excitation of electrons from the valence band. So we can see that the electron concentration will always be greater, and here for an n-type semiconductor the majority carriers will be electrons and the minority carriers will be holes. So this is the case of n-type semiconductor. So n-type semiconductor is formed by doping with pentavalent impurities. So we can generalize the band diagram of n-type semiconductor as EC conduction band edge and EV valence band edge, and EI will always be there in the middle. So actually this is n-type. So we are doping it with the pentavalent impurities. So to represent the pentavalent impurities or the donor impurities, we should draw a donor level. That donor level should be closer to the conduction band. This energy level is known as donor level. This is the energy band diagram of n-type semiconductor. So this is extrinsic semiconductor classification, that is n-type semiconductor. So next one is p-type semiconductor. Here p-type semiconductor is obtained by doping with the p-type is obtained by doping an intrinsic semiconductor with trivalent impurities. Trivalent impurities like boron, aluminium, gallium, etc. So here boron is added to the silicon crystal. So boron atoms are added to the silicon crystal. So the valency of the trivalent impurities is 3 and the silicon is 4. When the intrinsic material or the silicon material, the valency is 4. So the outermost electrons of the boron atoms form covalent bond with the silicon atoms, but there will be a vacancy, there will be a lack of bonding for the fourth electron of silicon atoms with the boron atom, because the boron has only 3 electrons that forms bonding with the 3 silicon atoms, and the fourth electron cannot form bond with the silicon atom. So there will be some deficiency. That deficiency is represented as hole. For a n-type semiconductor we have seen one extra electron. Here this semiconductor has a tendency to accept electrons. So there will always be a deficiency of electron, and that is known as hole. So this vacancy is represented by hole. So for a p-type semiconductor T is equal to 0 Kelvin, there will always be a vacant level, and that vacant energy level, that impurity level is known as acceptor level. So actually this is acceptor level, which means there will be some vacancies. So some holes will be there that will be closer to the valence band also. Some vacancies, or it has a tendency to accept electrons. So, and that acceptor level will always be closer to the valence band. So this is the case at T is equal to 0 Kelvin. So this is the structure at T is equal to 0 Kelvin. And if we increase the temperature to 50 Kelvin, we can see some bond will break in the structure, and some bond will break, and this electron will move towards the vacancy or the deficiency, and this electron will move towards this place, and we can see a hole will be created in the this spacing. So actually we can see that the hole is moving. Actually hole cannot move. So if we look at the structure, the position of hole is here, but after the temperature is increased, we can see that the hole position is changed to this. So here the majority carriers will always be holes. We can see the holes are moving, the position of hole is changing. So we are considering holes are also as a charge carrier. Electrons and holes are charge carriers. So this is the case. So if we keep on increasing the temperature, more holes will be created. So again, if we increase the temperature, then this bond will break, and electron will become free and a hole will be created. So this process will continue, and if we look at the energy band diagram at T is equal to 50 Kelvin, so if we rise the temperature, we can see here some vacancies are there. So electrons from valence band will move towards the acceptor level first. So it will occupy the vacancy at the acceptor level. So we can see there will be some hole formation in the valence band, and if we keep on increasing the temperature, again this electron will move towards the conduction band. At that time, more number of holes will be created in the valence band. So hole concentration is occurring at the valence band. Hole concentration is occurring at the valence band, and the hole concentration in the valence band will be greater than the electron concentration for a p-type semiconductor. So the holes are the majority carriers in the p-type semiconductor. So here actually the holes are increasing. Here the holes are increasing since the electrons are very less in p-type semiconductor. So holes are the majority carriers in a p-type semiconductor. So this is the energy band diagram and structure of p-type semiconductor. So we can see the final energy band diagram of p-type as EC, EV and EI. EI is always in the middle. So actually this is intrinsic semiconductor. So if we dope this intrinsic semiconductor with some boron atoms or trivalent impurities, so that impurity level should be represented, that will be closer to the valence band, and this impurity level is known as acceptor level, EA. So that EA will be closer to the valence band. So this is the energy band diagram of p-type semiconductor. So this is what we studied in this lecture, that is the different classification of semiconductors, intrinsic and extrinsic. Intrinsic means purest form. In that we should study the 2 points, that is at T is equal to 0 Kelvin, intrinsic semiconductor will act as an insulator, and at any other temperature, intrinsic semiconductor, the electron concentration will be equal to the hole concentration. Then the band diagram of intrinsic semiconductor, that is important, structure is not needed. Then next classification is extrinsic semiconductors, that is doping, the process of adding impurities to the intrinsic semiconductor. That process is known as, so doped intrinsic semiconductors are known as extrinsic semiconductors, and these extrinsic semiconductors can be classified according to the different methods of doping. So if we add pentavalent impurities to the intrinsic semiconductor, then that is known as N-type semiconductor. If we add trivalent impurities, then this semiconductor is known as p-type semiconductor. And one more thing, this donor impurities that we are using for N-type semiconductor are represented by NT, donor impurities, and the acceptor impurities are represented by Na. So Nd is used in N-type and Na is used in p-type. So example for Nd is phosphorus, arsenic, antimony. Then example for Na is boron, aluminium, gallium, etc. So these are the different classification of semiconductors. In the next lecture, we will study about the concept of effective mass, then Fermi level, Fermi-Dirac distribution, and that will be the next lecture. Thank you.